Welcome back to Arts Learning. In this video, we'll be going over circular motion, which includes centripetal acceleration, as well as what the centripetal force is. Okay? And we'll go over a few problems regarding that as well. So first, imagine yourself, right, spinning a yo-yo. You spin the yo-yo like this, okay? This is your center here. And imagine this is your yo-yo, it goes all the way around like that. Okay? So now, what force is keeping this yo-yo in orbit? Well, if you think about it, what forces do you even have here? You have the force of gravity, right, pulling the yo-yo down. But what force is keeping it in orbit here? The force of tension from the spring, right? So the centripetal force isn't a force by itself, like the force of gravity, the force of normal, the force of friction. It's just a representation of forces, okay? It's basically what a force does. Centripetal means it's kept in circular motion. Okay, you might have heard centrifugal, but centrifugal force doesn't exist. It's more of something we use to make equations more convenient, but centrifugal force doesn't exist. Centripetal force is what exists, okay? And what this force does is it pulls you inward. What do I mean by that? So, similar, right? This is a yo-yo here. If you take the velocity at any point on this orbit here, okay, so over here or over here, wherever, the velocity is always going to be a straight line because if you think about it, right, Newton's first law, the law of inertia, if an object is in motion, it's going to stay in motion, and if it's in rest, it's going to stay in rest. So over here, if the object is in motion, right, at that specific point in time, I mean, if you know calculus, you'd understand that even though this is circular motion, the derivative would be the tangential line, right? The slope of the line. What's the velocity here? The velocity would be tangential. Or in other words, just a straight line perpendicular to the path of orbit. This is your velocity. Wherever you are, your velocity is going to be tangential to that point, okay? So always just straight lines. As you can see here, everywhere I just drew straight lines, tangential to the point. Tangential means it touches that orbit at only one specific point, okay? It touches that orbit at one specific point and you can make a straight line out of it. Because even though you might think, suppose if you drop the ball at this point, right? Suppose the string snapped. You might think that it would keep going in a circle and you might like do something like that and go away. But it's actually just going to go in a straight line like this. Okay? Because that's the direction of the velocity. It's tangential. If you pause at that split second, your velocity is going to be a straight line, sending you to a straight place. And you'd understand more if you understood the derivatives concept from calculus, right? Straight line is the derivative of the position. In this case, when it's circular, and then you can find out that it's just a tangential line there. The slope of your position is your tangential line. So if you don't understand a lot of what I said, I recommend you look over that concept. Okay? So now that we know that velocity is a tangential line at any point to the place the yo-yo is traveling, right? Then what else do we know here? We know that some force must be keeping us in orbit, right? So we might be going like this, but some force must be keeping us in orbit. What is this force pulling us towards the center? This force is going to be pulling us towards the center, okay? It's our force centripetal, pulls us towards the center. And in this case, because of the rope, it is tension. So centripetal force isn't its own force, it's just the name we give to a force that happens to pull things into orbit, into the center, okay? And why do you think that force would be straight towards the orbit. Because imagine that, for example, your velocity is here, right? Think about it. If your force was just in this direction as well, then you understand that if the force and velocity are in the same direction, the object is going to accelerate in this direction, right? Force is equal to ma, force and velocity same direction, the object will accelerate. If the force was in this opposite way, the object will decelerate, but it's still going to have some change in velocity, right? Because force is equal to ma, and since the object has mass, that means acceleration must be there, which means the velocity must be changing. But we know that it's going to be at constant speed, right? When you're spinning a circle, I mean, I guess in certain circumstances you can spin it faster and faster, but imagine if it's in constant speed, right? Imagine a car drifting. It doesn't change speed while it's drifting, it drifts at the constant speed, right? How do you keep it in constant speed? The force has to not interfere. We don't need to have an acceleration, right? I mean, inevitably we'll have an acceleration because even though the velocity here is, straight line, even if you do a velocity vector here, the magnitudes of this vector would be the same, but since it has a different direction means different vector, hence acceleration. But think about it in terms of speed, right? How do we keep the same magnitude throughout? Our force shouldn't interfere, right? The force shouldn't interfere. No interference with the velocity, with the direction of velocity at least, or the object, right? So what's the only point at which that can happen, right? Because even if, for example, my force was like this, then I would still have a component of force in this component of velocity. Even if my force was like this, I would still have a component of force in the component of velocity, right? Vertical components here that change it up. So my force here must be perpendicular to my velocity. That's the only circumstance under which this force has only a horizontal component and this velocity has vertical components, so they don't interfere with each other. And hence, the object doesn't accelerate. When you're looking at constant speed anyway, okay? So at this point, you might be like, okay, well, the object still has some horizontal and vertical component because this isn't purely vertical as well, right? But so the force must be in this way. And you can imagine that so even though it looks like that, if you rotate it here, you're still going to find out that the components don't interfere with each other. You just have to rotate your view a bit. It's a bit hard to explain, but you just need to rotate your view, okay? Just keep in mind that the force and the velocity, in this case, for centripetal acceleration, are going to be perpendicular, all right? Now let's go over the equation. Your acceleration centripetal, so not your mass or your force, right? Just your acceleration centripetal is going to be velocity squared, okay, over r. V stands for velocity, obviously, and r is radius. So radius is in the radius of the circle you're spinning around, okay? And think about it. If your acceleration was this, what would your force be? You could just substitute your force centripetal to be mass times acceleration, or velocity squared over r. And remember, the force centripetal isn't a force on its own, right? If you think about a planet, we don't have a centripetal, there's no force called a centripetal force helping us orbit around the sun. It's the force of gravity, okay? So in that case, our gravity force would be a centripetal force, okay? It would be one of them. In this case, it would do that job of helping us rotate in a circular motion. So this is just for, in general, the equation for centripetal forces, all right? And now we're going to look at, so this is net force here, obviously, net force centripetal, m times v squared over r. And then the velocity here. So this is one scenario, okay? This is one scenario. There's another scenario. So I'm going to give you both the formulas you can use for centripetal motion. The other scenario is velocity is 2 pi r over period. Where is this coming from? Velocity is the distance you travel over the time, right? So the distance, imagine you travel the entire circumference. That's 2 pi r, right? And then what is the time you travel that in? That time is just your period or your big T, right? If you remember, we use the same big T for period and time of flight. And then you could just substitute in that here. Acceleration centripetal is equal to v squared over r. So 2 pi r over t squared over r, or 4 pi squared r squared over t over r, or just 4 pi r, so sorry, pour 4 pi squared here. 4 pi squared r over t squared. All right, and that's, there you go. And then you multiply this by your mass to get your force centripetal. So this is one scenario, okay? This is not, I'm not saying, this is when you need when you're given the period and the circumference or the radius, and you can figure that out. These are both different scenarios. Velocity squared over r is the general formula. And sometimes when you get lucky, you can use velocity is equal to 2 pi r over t. And I just show you why that's true, right? And I'll include a derivation for this formula because I don't want to just give it to you. I'll include a derivation for this in my extras video section. So be sure to check that out on artslearning.com. Right, so let's try a problem. Accelerations are a 0.5 kg ball. This is a 0.5 kg ball. Moves the velocities 4 meters per second on a string of radius r is equal to 0.8 meters. So the radius is 0.8 meters and our velocity is 4 meters per second. We need to find the centripetal force. So we know force centripetal is mass times the velocity squared over our r, right? Because acceleration centripetal is v squared over r, and force is equal to mass times acceleration. So we can just substitute that into here. Okay, so now we know that. And we can substitute in is equal to 0.5 kgs times 4 meters per second squared over 0.8 meters. All right, and this should give you about, so let's see, it's, this by itself is 20 meters per second. 20 meters per second squared, right? Because the meters cancel out with the meter squared. And then you multiply that by this 0.5. So let me bring that up here. Times 20 meters per second squared times this 0.5. Or in other words, just 10 newtons. And always, centripetal force is always inward, right? Towards your center. That's what's keeping you in orbit. Otherwise, you'd be floating away. Just like this. Okay? And remember, if I release this ball, it would be going in a perpendicular direction. Okay, not like this, not like like that. It wouldn't have any circular motion, just a straight perpendicular direction because the velocity is tangential. Okay? And similarly, if I release the ball somewhere over here, it would be going in that kind of direction as well. I mean, there's two tangential points, right? So it depends on which way I'm spinning. If I'm spinning counterclockwise, then obviously it's this velocity here. If I'm spinning this way, it's going to be this velocity here. It depends on which way I'm spinning, but it's whichever one is tangential, okay? And then, I mean, this is just an extra. If you wanted to find the period, you could just do 2 pi r over t, big T, right? So big T is equal to 2 pi r over v, and then you can get you 1.26 seconds per rev, or revolution, okay? The revolution just means one revolution across the circle. I mean, one movement around the circumference, okay? So a 1200 kg car rounds a curve of radius, so let's look here, of radius, let me draw this car, and it's going to be a weird drawing because it's going to have to round the curve, right? So round the curve with a radius of r of 50 meters, okay, with the mass of 1200 kgs, and then a velocity of 20 meters per second. We need to find the centripetal acceleration and the friction force needed, okay? So in this case, imagine that, okay, so it's a bit hard to draw, but imagine that there's a sudden curve in the road, right? Like a U-turn sort of thing. Your car is over here, and in order to make this orbit here, you need to have a centripetal force that's pulling you into the imaginary center, okay? Otherwise, your tangential velocity would just send you straight forward, right? So you need a centripetal force because it's a circular motion. And what's that centripetal force going to be? Well, think about it. Gravity, not gravity, right? Gravity, we're already on ground. Tension, there's no rope here. It's got to be friction. Friction is the force keeping you on the road surface, right? It's the force that's going to resist your movement, pull you inward, but also keep you in that orbit. It's going to resist your motion in other way. So you just got to cancel out forces until you figure out which one is the one. And it's usually not going to be the normal force, right? It's just forces that correlate directly to motion. So motion forces. Okay. So centripetal acceleration first is going to be v squared over r, so 20 meter per second squared over our r, or 50 meters. So this is 400 meters squared per second squared over 50 meters, okay? So then this is 8 meter per second squared. That's our centripetal acceleration. The force of friction needed here. So you might remember that force of friction is mu times normal, right? And you could use that, but the thing is we don't have a mu. What do we also need to know though? We also know that the force of friction is our centripetal force, right? Our force centripetal. So we can just use that there. But, this is going to be equal to force of friction. It's just the force of centripetal. What's a centripetal force? It's this acceleration times our mass. Or in other words, it's just force of friction is just mass, which is 1200 times 8 or 9600 newtons of friction force. Okay? All right. And then let's try let's try number 2. Yeah. A ball on a 1.5 meter string makes one full revolution every 2 seconds. Find its centripetal acceleration using a is equal to 4 pi squared r over t squared. Okay, so they literally gave us the formula, right? A is equal to 4 pi squared times r. So what's our radius here? The string is 1.5 meters, so if we're rotating it, right, then the radius is basically the string. It's the length of the string. So that times 1.5 over t squared. So t is a period, but that's 2 seconds, so 2 seconds squared, right? And that should give you about 14.8 meter per second squared. All right, and then let's try one more. Actually, 2 more. A vinyl record spins at 45 revolutions per meter. Or per minute, sorry. Per minute, here per minute. Almost confused myself. Revs per minute. A point sits r is equal to 0.14 meters from the center. Using v is equal to 2 pi r over t, find the speed, then its centripetal acceleration. Okay, so v here, which is our speed, is equal to, velocity in this case is speed, right? Because we're not looking direction. 2 pi r, and r is 0.14 meters. They just gave us the radius. That over our period, which is how long it takes for something, right? And this one is going to get a bit complicated here, so stay with me. 45 revs per minute. So our period is basically 45 revolutions per minute, okay? Now we need that in seconds. We need how many seconds it takes for 45 revolutions. So Or we just need to convert it to second. We know 1 minute is for 45 revolutions, and then we can just multiply that by, so we need a minute to cancel out here to make a second, right? So 60 seconds per 1 minute. The minutes cancel out, and you're left with 1 second, or let me write this out clearly so you can see where I'm getting this from. 60 seconds per 45 revolutions, or 1 second for, actually just, we can just divide 60 by 45, right? And that's the time we take for revolution. So let's see, what's that gonna give us? That's gonna be, let's see, that 60 divided by 45, so 0 divided by 45. It's a repeating decimal of 1.33, right? 1.33 seconds. And then our velocity, so we can get the velocity from this period, right? This isn't some random stuff. This is our period here. So this is our period. Our velocity then would be 2 pi times our radius of 0.14 over our period of 1.33. So that's about 0.66 meter per second. I was almost about to say squared, but it's just 0.66 meter per second, right? All right. And then, is that it for this one? We needed centripetal acceleration as well, right? Not just velocity. So acceleration centripetal is mass times, whoops, not mass, that's the force, right? So velocity squared over r. R, 0.66 squared, that's a velocity, right? We just figured that out, over our r of 0.14 meters. And this should give you about 3.11 meter per second squared. Okay, there you go. That's the other question. Now your last question here. A 0.2 kg ball is swung in a horizontal circle. Okay, which force component supplies the centripetal force, and what balances gravity? So basically what they're saying here is you're over here, right? And you're spinning this ball, but you're not spinning it like this way. So think about vertical circle is, you're spinning it vertically, like think of a roller coaster. But a horizontal circle is more like a hula hoop, right? It's level with your body. You're just spinning it horizontally. It's not vertical. So which force component supplies the centripetal force, and what balances gravity? So we know that T horizontal, right? So this tension, horizontal, is our centripetal force, because this is the rope, right? What's the force of the rope? It's a tension. This force is what's going to be pulling us inward wherever we are. It's going to pull us inward, right? The force of tension. And then what's going to balance gravity? Well, our horizontal force is T, tension, right? Do we have a vertical force for tension? Well, you might think that we don't, but the thing is we have to, right? Otherwise, what force is going to balance here? Air resistance? No, right? Our vertical force is going to be our T vertical, the vertical component of our tension. So our tension here will be having two components, okay? Otherwise, think about it, right? Gravity will be able to pull us down. It'll be able to accelerate downward if we don't balance it like that. That's why whenever you hold a string, hula hooping is difficult because you need to balance both vertically as well as horizontally, right? And in this case, the string here, try imagining it, right? Rotating it around in a vertical circle is much easier than a horizontal circle, because for a horizontal circle, you need two components. You need the tension horizontal to balance your centripetal force, right? To pull you inward. But you also need a vertical component of your tension to balance your gravity. So when just imagine, it's a bit hard to rotate it that way, right? you have to strain your hand and hold it very harsh, and you have to pull it very, very hard. So it'd be T vertical balances gravity, right? As our vertical component, because gravity is in the vertical direction, and our T horizontal balances our not balances, it is our centripetal force. Okay. So in the next video, what we went over today was just basic introduction to centripetal force. Okay. There are scenarios which we'll go over later. It includes something like this. You have a vertical circle, right? And at some point you'll have the force of tension as your centripetal force, but you'll also have the force of gravity pulling you downward, right? So then if you have your centripetal force greater than your gravity, you'll have an acceleration. So you need to incorporate this gravity into your centripetal force. I'll show you how to do that in the next video. So stay tuned for that. And thank you for listening. Subscribe and like to Arts Learning if this helped you. And make sure to check out my website, artslearning.com, for more PDFs and resources to help you out on your physics journey.